All right, we're back. Mardi Gras, blah, blah, blah. You're not going to see the other parts. You're going to go away forever. Wouldn't hear it anyway. But my presents for you are, so homework 3 is not out yet. It starts like next week or somewhere in between now and then. And I'm actually removing one of the homeworks from this year. So you have one less. And it gets better. Clapping. It gets better because my intricately detailed homework, my point system for class goes up to 100. To not screw it up, I'm going to give you all 9 points for that homework that's not there. All right? So does that bring the beast? No. So, and it gets better. What could top that for class? Next week I'm not going to be here. I know. I'm going to Miami. Yeah, I'm going to Miami. So, yeah, I have a conference in Miami next week. So it's a festive week. What's that? No class next week. So, yes. So what that means, though, is that I will have, instead of class, I'll have a little lecture. It'll sort of give you, it'll be like a brand new online lecture that, you know, you could like have class observe for. It'll introduce homework 3, get you set up for it, and you'll start on that. Okay? Yes, question.
This is unrelated to that.
Okay.
Is Lisa teaching the multi-level modeling class this fall?
No, not, I'm sorry, pardon me. This fall, she's at the end of her year cycle. Next fall, she'll be teaching the SEM, what we call SEM, latent trait measurement and structural equation models. And it's cross-listed with child language and educational psychology.
So the multi-level modeling is
The following year, yeah, it's a year from fall it starts. So that's one of the problems. So Lisa's teaching schedule is 3 courses every 2 years, which is 3 semesters on and 1 off. So she does a year-long sequence of multi-level every other year is where that works out to be. So sorry about that. No problem. If you want to catch up, though, the nice thing is you can still just follow along her class online. She'd even give you, she built the homework system, so she can even give you a login for it if you want to practice this. Just email her. She's done that before with people. So anything else? Other questions? So want it to get better yet. My travel schedule is getting crazy because I go to Miami, and my punishment for going to Miami is I get to go to Wichita the following week. Anybody from Wichita? I'm sorry. Actually, kid you not, I did spring break in Wichita once. That was awesome. I had a colleague that worked at Wichita State when I was over in the psych department, and so I went down and we had spring break in Wichita. It was awesome. But no, I won't be here for the following Tuesday as well, but I plan on having a Zoom class that second week. But look for information about that. So it'll be class online on Zoom. I'm going to record it on Zoom. That means if you're on Zoom with us, you don't have to show your screen or anything like that. You can mute yourself. You don't have to be on there. But if you do talk on there, it'll be recorded just like we have in the lecture here. So I'll give you that in an email or an update for an announcement. So my life is kind of crazy these days, but things are coming up. So can I level with you for a little bit? All right. Kind of embarrassing. Just teach you. So this morning I'm doing my typical Tuesday deal where I'm like, shoot, I need to make an online lecture. So, I had already prepared the content, but it's getting myself to sit in front of my computer and talk to it. Like talking to myself is really difficult for me for some reason. And so I start recording it. It's about an hour and 15 minutes in. And I realize I'm making a mistake somewhere. Like I say the proportion should be 0.55 and the computer says, actually I say it should be 0.55 and the computer says it should be 0.45. I'm like, where is this problem? So I have to stop the lecture, go through all my notes, rediscover the world again, find out I had a typo in my slide. I missed the negative side, right? So I recorded the end of the lecture, and now the reason why it's not up is because I have to convert them to MP4, splice them together, and put them together. So rather than lead you astray, I screwed up. And yes, it happens still. So if you think statistics are challenging, they don't stop being challenging at some point. Okay? Sound cool? All right. So that means I won't put the lecture up until probably tomorrow morning. I'll send out an email to everyone when it's up, and I also won't put the quiz up for next week because I don't want you looking at the items and going, oh, what's that? And then like not having the lecture to tell you what those are too, right? I don't want to increase your anxiety too much, although I know I do that. There's a tension in here. It's like the dentist's office. Anyway, so does that sound good? Any questions, comments? So a couple thoughts. I pushed back the content last week to try to let you focus on the homework because I really wanted to slow down. Interactions are so key to understanding research and to doing good research that I really want you to have a chance to learn it. And I'm really happy I did that, right? I feel like we're not piling things on yet, although it may feel like that still, but it's not as bad as it could have been. But a ramification of that is rather than giving you like 18 things to watch this last week, I put 2 down. Least squares, distributions and then least squares. And that means that this week we had to have this gap. What would have been in this week before would have been the logistic regression generalized models, which would have led off to this homework, but just pushed everything back a week. I'm totally okay with it. Doesn't bother me. Happy to do that. But that means this class is going to be a lecture on maximum likelihood. And I'm really happy about that in some ways because I'd like to see you when I lecture. Rather than just lecturing to my computer, I like to look at you because I try to pay attention. Honestly, I do like this visual scan. Now, it's harder in this room because it's just so steep. I don't know if you notice. When I come in, I put my head down. I'm like trying to get my stuff ready. And eventually I take a peek. Oh, yeah, they're here, right? And so it's like that's sort of how it is. It's like overwhelming just to see you. So I'm going to try my best to make this work. But maximum likelihood is a really difficult topic, but I don't want you to learn the math behind it. I don't care about that. I want you to learn the concept, why we use it, why it's important, and what to do if it breaks, essentially, right? So that's sort of the big picture for where we're going with all of this, where that happens. But to lead off, to try to finish up the business we had before, let's talk about the quiz that was online this week. Going to get us into this. Have to remember what's online this week. All right, it should be re-enabled again. You should be able to see quiz 4. And let's take a look at these questions, shall we? Question number 1, a random variable has a distribution of possible values. What name is given to the range or set of possible values? We want to take a stab? Sample space, right. We don't often talk about sample space in stats classes where we do applied statistics. You may not have heard about it much. You may have heard about it like in very intro stat, like when you were talking about rolling a die or flipping a coin or something like that, but it doesn't show up a lot in the applied statistics. But I want to bring it back a little bit because we quickly run into situations in data where our data doesn't fit our model somehow. For instance, you have a binary variable you're trying to predict. Anybody have an outcome that they have that has two levels, 2 categories? Graduation from high school, successfully find a job. Anybody have one of those? Anybody want to share it so we can? No? Yeah, Ahmed.
Yeah, we do have it, like with the theoretical system, like for central awareness training, students like success or fail in the exam.
So succeeding or passing exam or not passing an exam, right? So let's imagine you want to take that pass-fail of some type of exam. Could be a lot, anywhere. That seems to be fair with all of us, right? And you want to model that somehow. Maybe you've got some type of brand new way of teaching the class or the content. And you want to see if people who are in this brand new way might perform better than someone that might be in the old way, right? Can't easily put that variable into a linear regression or a linear model, general linear model, that assumes that outcome is conditionally normal. Right? Remember, the assumption is conditional normality, meaning once we predict the outcome given, let's say, the type of teaching you're in, teaching style you're in, the remainder from that isn't really plausible to be normal. It's either a 0 or a 1, right? So what do we do in that situation? Right? Well, there's lots of cases in data history, in the annals of bad statistics past, where we had to do something, right? And oftentimes, we may have another type of outcome. Maybe we have an outcome that's somehow has some heavy skew to it, or it plausibly is continuous, but we fit an analysis to it, and we look at our residuals, which I think is at the end of one of the lectures we had this last week, where you can do a residual plot and see if they're normal. The QQ plot, that thing, it doesn't look normal, right? So if we're concerned about that, what do? Right? Most stat classes I've been in and been around and hear about say, oh, transform the data. Problem isn't with the statistics, problem's with your data. But the problem with transforming your data is that you often lose the effect you're most interested in. You're changing the effect by transforming the data. So the philosophy I give and the philosophy I think we're moving toward as a field in statistics is more, don't transform the data, change the assumptions of the model. And one of the primary assumptions of the model is the sample space. Does the range of possible values that you assume with the distribution mirror the range of possible values that you have in your outcome? Right? And in the case of this pass-fail for the exam that we talk about, it's not plausible that pass-fail, even once we predict it with the type of teaching method a person received, it's not plausible that what's left over is normal. Because there's two values there, right? It's discrete. It's a categorical variable. It's not continuous. So we have to change the distributional assumption of that, and it starts with the sample space. Right? So that's why I put that there. That's why I'm bringing this up, because when it gets to your data, yes, if you have a continuous outcome, more often than not, the linear model works well for it. But increasingly, we're finding places where we don't, or we might have a categorical outcome with 4 levels. Do we pretend it's continuous? Do we switch the distribution? So what we're going to do is switch the distribution. And again, the first place to think about that is sample space. Right? We want to make sure we pick a distribution with the right sample space. Good news is there's some big popular choices to choose from. So it's not like completely like I have no idea, I'm just going to randomly go to my wheel of distributions and grab one. There's some very specific types of distributions that go with different types of outcomes. Generally speaking, your outcomes that are 2-category have one type that we're going to get into with logistic regression. If you have a fixed set of categories, maybe 5 or 6, that's in the same family as the logistic regression. If you have a count variable, like how many cigarettes did you smoke today? How many beads have you received today? Right? I have received 2. Anybody else receive beads today? No, and I got them for eating at the union, so that's fair way. What's that?
Outlier.
That's an outlier, right? But there are people like my mom's picture in New Orleans today that have beaucoup beads, right? And that's a big thing. So to think about it, right? We have a bunch of zeros. It's that type of variable is different than a categorical outcome with 4 options, right? Because there's no upper end to how many beads a person can receive. I mean, I guess there's practically one, but we could find people who have hundreds of beads, right? But there's a bunch of people who have 0. So how do we model that? So that's a count distribution, right? Frequency. There's different distributions for that, different families for that. Or you've got distributions where you have skewed data or censored data or continuous data that might, like reaction time. That's a good one. What do you do with reaction time? Clearly, it can't be negative. I guess maybe an ESP study? No, never mind. Paranormal, did we do that? Anybody study paranormal? Thinking Ghostbusters, right? Like the first one. No. Then, like you have to have something that starts above 0 and usually has a very long tail, positively. Yeah.
I just got a question, like, say, how, I know these assumptions about the different distributions, but like when you use certain functions in R, for example, or SPSS, those functions take on those, have their own, like, automatically use the distribution.
That's right. Mm-hmm.
Which they kind of derive
That's right.
and algorithms from distribution.
Exactly. That's exactly it, yeah. Yeah, and actually that's what we're leading into today's lecture, which is the process of maximum likelihood does not assume a specific distribution, it's just that a distribution exists. And so if you have a distribution, if you can pick it, they kind of work the same. It's a little bit weird to think about, but the height of the distribution Like you plug in a piece of data and you see how tall it is, it's a likelihood. And we go through a process of building a function that we use to maximize a likelihood, and that gives us results that we can believe in. So really, you can pick a distribution, or you can find out why there's different distributions out there and different algorithms, is because it is conceptually the process of saying, I have to pick a distribution, but once I pick that, I can find good statistics that go with it. So that's a good question. That's right. Yeah. Well, that's where SPSS starts to break down. Its ability to do what we call generalized models is somewhat limited. There are some that it does and does fine. Honestly, the package that I found that does really well with it is SAS. SAS does great. It has a set of procs and SAS that keep things very similar. The problem I have with R is that there's a package over here that does it one way, and there's a package over there that does it another way, and so it's very disjointed. And so in my own mental notes for class, I want to sort of build a package that does it consistently, not the right way. They're equivalent. They're just translations of each other. So it's a little bit easier to understand what's coming out of it. But the conceptual part of it, the part that I want you to understand is, when you're thinking about what distribution do I use, you sort of think about the space of values that your dependent variable might have, or a set of dependent variables, and you try to match a function to that space. And you say, oh, I have two categories. Okay, I'm going to use this function over here that assumes two categories. Or I have this reaction time, so it's a skewed data that, so I'm going to use this function over here, or this option on it to use it for skewed. But the bigger picture is you're not touching your data. The data are still in their same format. But through what we're going to talk about today and what's online after this, the process allows it to kind of take the data and take the statistics and map it onto the space of the range of the data so it fits it. So is that cool? Does that sound fun? It's harder. Like, it is harder. It's a level of complex. Like, if the world were just what you learned in 810, I don't know if you got into logistics. Did you get logistic regression in 810? Anybody? No. Okay. So linear regression, a little bit of ANOVA, generally speaking, right? If it were just that, it'd be a lot simpler, right? But I'm going to teach you this in a way what I'd like to try to narrow the realms of possibilities. The interpretations are largely the same. There's now just an additional step that go with them. So go with there. But the process of estimating it is, again, formulaic. You need a distribution to start with. Once you have a distribution, if you're wanting to code it in R, you build this function and find the maximum of it. Anyway, you don't need to do that. Someone's already done that. So are we good? Sample space. That's why I put it there. For estimating, question 2, for estimating general linear models, models with one outcome assumed to follow a conditionally normal distribution, least squares estimates have good properties because, anybody? They are identical to maximum likelihood estimates. Yeah, this is the one interesting part about learning statistics, particularly when you start with the linear models, is that you may have heard of least squares in 810. Did you hear about that? Kind of, we're minimizing the squared residual. How did you like my minimizing the squared absolute residual? The absolute. Did you like the L1, the quantile regression I showed you? I think that's cool stuff. Anyway, it's just change of an option changes a whole bunch of stuff you can do with it. But they are identical. But the convenient thing about it is you're doing maximal likelihood and not knowing it, and so that's part of what happens. Where least squares estimates start to have an issue is if we have multivariate data. So if you're collecting more than one outcome per person, right? So you might have whether a person passed or failed a class, and you might also have like their score on some type of like licensure exam or something like that, right? So you've got two pieces of information that you want to go and model about a person. The least squares estimates start to break down, particularly when you have one of those pieces of information missing. Missing data is harder to deal with. You have to typically throw out the whole set. So maximum likelihood helps give you a little bit more flexibility with missing data when you have least squares. For the regression ANOVA case, where there's only one outcome, it doesn't really change much, though. How are we doing? Okay, there is a point to all this, I promise. So all these questions made sense? Are they better than or worse than the interaction questions? Better? Easier? Conceptual, right? So my promise to you, though, is that hopefully by the end of the semester, interactions will be so routine to you that you'll think the opposite, right? Because there will be interactions in the next homework, I promise. But that's not to scare you. It's to give you another chance to work on it, right? And it's, again, I'm trying to do it in a format where you're not going to fail, I promise, right? You've got my help, you've got Jihong's help, you've got each other's help, right? I just want you to learn it because you can. I know you can. Okay, questions then. All right. I want to leave that site. Shall we get into lecture? Let's do this. Actually, I might do it this way. Give me just a second here. Should have thought of this ahead of time and prepared it, but such is life. Should have done a lot of things ahead of time. You know that feeling? Thanks for bearing with me. Not helpful. Here we go. I'm going to draw on my lecture because I like drawing here. So we're going to do this on PowerPoint. And while we're working on PowerPoint, I will also pull up the R file on my slides here to go with it. So start to screen mirror. Going with PowerPoint. Have my Apple Pencil. Here we go. Can you all see that okay? All right, here we go. So we're going to talk about maximum likelihood estimation. This is fun. This lecture, we're going to talk about the basics. Again, it's conceptual. The technical side of this is really complicated, right? The process that we're going to use to find a maximum relies upon calculus. I don't want you to know, you don't have to learn calculus to do this. You don't. But just the concept of it helps. Now, for those of you who love technical things, if you'd like to learn more, you're welcome to come talk to me. I'm happy to tell you that. You know, try to recruit some future students from this class, so you never know who you are. That was me, by the way. I hated math until I took statistics. And I get it. The light bulb came on, so if that's you for math, you're like, hey, now I get it. No, I'm just kidding. So we're going to talk about maximum likelihood. I find that it is still, I keep saying this, it's still the gold standard for what we do in statistics. We want estimates to be maximum likelihood or likelihood based, because technically speaking, the Bayesian estimates that we get coming up that seems to be very popular or increasing in popularity these days actually derive a lot of what they get from the same function that we get in the maximum likelihood estimates. They work the same, so they have a lot of the same properties. And technically speaking, least squares can be shown to have some of the same properties too, although it's slower to get there. So maximum likelihood have these properties we can count on. There's additional estimation information that we get from using these tests. We get model comparisons using likelihood ratio tests. So if you have any two models, you can always compare them using these likelihoods, the log likelihoods from each model. This is great because I mentioned before, in regression ANOVA, you had your ANOVA table, right? And you could always compare two models that were nested by taking the sums of squares and doing something with them. I totally forgotten what that is, by the way. I teach this stuff. But ANOVA tables go away. So now what do you do with it, right? Forget it. If you've got maximum likelihood, it doesn't matter if your distribution is conditionally normal or something you've never heard of before. Anybody heard of Cauchy? The distribution called the Cauchy distribution? No one's heard of Cauchy, right? There you go. Don't know what it is, but estimated with MLE, you can make a model comparison. It's a likelihood ratio test. It works the same way. Compare log likelihoods, look at the difference between the negative 2 times the difference between the two, follows a chi-square distribution, and you can always figure out whether your new model that has more parameters fits better than your simpler model. It's pretty cool. Wald tests. Inadvertently, you were using these already. Those are the tests that are formed when we take a parameter, like a beta weight, and divide it by a standard error. Right? So if I take beta divided by the standard error of beta, do you remember that output from R? When you do the summary table, they have beta weight, they have standard error, They have a t-statistic. Well, that t-statistic came from the beta divided by the standard error of the beta. And they compared that with the t-test. That is technically a walled test, and it comes from the properties of maximum likelihood as well. So you're already using that. So now, again, let's imagine someone says to you, there's this great new thing in research. It's called Cauchy distribution. We're going to use it. We have an MLE for it. We're using maximum likelihood. You're like, oh, I know how to do my parameters. They work the same. I can go and figure out whether or not they're significant the same way I could figure them out as I would in linear regression. I take the parameter, divide it by the standard error, and I can tell it's a significance test. So we get this somewhat constancy with what we get from this. We also have something called information criteria, which are like likelihood ratio tests for non-nested models. But I'll talk about nested and non-nested models as we go forward, what those two differences are. How are we doing so far? This is an intro. Too much in here. We're also going to talk about maximum likelihood estimators for general linear models for where we go forward. But here's a data example today. I think I used this in the least squares example too. I have 5 scores because I want to make this simple so you can see the math behind it. You can play with the R output or input. It's just more conceptual again. It's to draw pictures. But imagine you have an employer that's looking to hire employees for a job where IQ is important. We have IQ measures on 5 of their employees. We have 5 job performance measures as well. And we see these data. These data, by the way, came from Craig Enger's Missing Data book. So it's a good book. I have some of the chapters I assign later in class. So we'll talk about missing data later on. You'll see this again. But it just gives us 5 observations to play with. And again, we talked about this in least squares. Least squares was a way that we estimated things by minimizing something. Maximum likelihood works by maximizing something. Seems pretty straightforward, right? There's another process that's out there where we simulate data to sample things. That stuff is very new, labor-intensive on the computer's part, but it's pretty cool. We'll get to that later on and why we'd want to use that. So maximum likelihood here show up, and you'll get names like maximum likelihood estimates or just ML. Just say it like it's a word, like a name. I almost, named my son Emil. That'd be a good name, right? I got overruled. No, actually, I'm proud I say I proposed both of my kids' names, and they were not rejected. So that's good. Residual maximum likelihood. Heard of that one before? I don't know if you've heard of that. Sometimes if ML is Emil, residual maximum likelihood has to be REML, and you're right about that. You may hear people also say full information maximum likelihood. Have anyone heard that one before? That one's FIML. Kid you not. There may be a robust maximum likelihood, but that is not RUML. That is robust maximum likelihood still. We have an odd field. Okay, questions, comments, tour of estimation? Got it? These are the properties that why we use maximum likelihood, because if several assumptions are true, then we get these good properties from what we've done. Now, these assumptions in statistics go by the term regularity conditions. Is that not terrible for a name of something, or what? Oh, yeah, if you meet the regularity conditions, then this happens. These assumptions are pretty broad, though, and most of them still hold for most of the data that you have. Several of them are things like if you're trying to do a walled test, like the parameter can't be on its boundary of where it's allowed to be, like if you're trying to test whether a variance is equal to 0, that sort of violates one of those conditions. But generally speaking, this holds for most of the data you are going to collect in what you do. So one of the big ones, by the way, is your model fits the data, which is a brand new topic that we have to worry about when we get to modeling more than one outcome. So model fit becomes a big one. But that's later on. I don't even want to go down the regularity conditions. It's just, generally speaking, we sort of take it for granted that we're meeting them. Hooray. All right. So if that happens, we get these 3 cool things out of it. We get consistent estimates, or what we call asymptotic consistency. And this is the key about maximum likelihood. This word asymptotic. What am I talking about there? What? That means as n, your sample size goes to infinity, literally. Can you imagine collecting infinity? Probably feels like that, right, already? Like for your data, it's practically infinity. That's where the word, if you've ever heard of the counter to Bayesian statistics is something called frequentist statistics. And that's where this word comes from. It's the n being large, kind of this replication idea, frequency, right? So when you see asymptotic, that means, oh yeah, my sample size, cool, all right? So as your n gets big, you get something called consistent estimates. Consistent estimates are awesome because that means what ML tells you is that as n goes to infinity, the chance that you discover that the estimate becomes its true value goes to 1. The probability your estimates become their true value is 1. So you get the right answer. Ooh. You like to be told that, right? Like there's a right answer for your estimates. As your n goes up to like your population size, you're going to find the right answer for your statistics. That's good, right? There are estimators out there, there are things that people use that lack consistency. Yeah, Sammy. It's different than power in that your parameter might converge to something that's 0. It's true value. Like if your power is testing whether like a beta weight might be statistically different from 0, but your true value of the beta weight in the population may be 0. So it's going to converge to 0. It doesn't matter how many people you have. 0 is still 0, right? It's just not related to what you do. But power would be trying to get a guess as to how much sample size you need to determine whether it's not 0. Right? So it's a little bit different in that. This is more thinking, if you could collect infinite data, what would happen? Right? Nobody can collect infinite data. We all know that. But it's sort of like we'd like to know if we could, we'd get the right answer. And that's what this is trying to say. So it sounds like a big thing, right? You'd want to know. That's sort of the tug and pull that sort of is at all the stat classes. Sample size. How much sample do you need? Anybody want to offer how much sample size they need? Anybody? 20. I like that one. Anybody work with a stat person? You know what the answer is from the stat person? More. How much do I need? More. Always. I have 200. More. More. Right? It's always more. That's the answer. That's usually because of this. Okay. But point being, so again, nobody can collect infinite samples. What this is talking about is, if you could, would you get the right answer? Think about what would happen if you couldn't get the right answer. What's that tell you? Oh yeah, your sample size, it can be infinite, but you're still not going to get the right answer. That's not good, right? No, but there are estimators out there that aren't asymptotically consistent. One of those that exists is something called joint maximum likelihood in psychometric models, where this happens. You've taken some of our psychometrics courses, you may have heard of item response models, briefly. Some of the first estimators in item response models were joint maximum likelihood estimates, and they didn't have the asymptotic consistency. So that means, yeah, you could collect a big sample and you wouldn't get the right answer. That's not good. Why are you collecting the sample in the first place? You probably said, right? Okay. Next, normality. As n is increasing, the distribution of your parameter, that's kind of what we call the limiting distribution of the parameter, converges to this normal distribution, right? So now, when n hits infinity, it's like it's sort of the normal gets pushed, smaller and smaller, smaller variance, smaller variance, smaller variance. But this property helps give us those Wald tests. So if we know the parameters follow a normal distribution, we can use some type of version of that, usually a z-test, sometimes a t-test like we saw in regression and ANOVA, to give us an estimate of the p-value of whether or not that parameter is significantly different from 0. And there's other things we can do with it as well. So for instance, if you have a set of parameters you want to test simultaneously. Remember in, was it last week, I sort of had an impromptu discussion of the factor option in R, and I showed how if we called a variable a factor, it coded it for us, but it gave us this multiple degree of freedom F test. that multi-degree of freedom F-test is important because remember in your homework, or in homework 2, in the categorical variable, when you put it in, when you coded it yourself, you only got a test of the parameter against the comparison of that group versus the reference group, right? Or in the interaction, that's also the same case. So you couldn't tell overall whether the group, whether the entire parameter was significant, like an omnibus test. But there are multivariate versions of the Wald test that would do that for you. Right? You get multiple degrees of freedom at once, test and effect. So it's all based on this asymptotic normality, which is nice. Pretty good. Questions? Okay, finally, efficiency. We all like efficiency, right? Makes you think energy. That's the first word that comes to my mind. Anybody else? Anchored it now, right? Basically what we're saying is no other estimator gives you a smaller standard error across the range of possible values than the maximum likelihood estimator does. Now that's cool, right? Because now that means, yes, you are going to get a good result that is better than it would be if you use something else. Now what else is there? We've sort of been using ML for the whole way. We kind of keep you off of those other things, but they do exist, particularly when you get more and more complicated models. Yeah, Sammy.
Do they expect you to check all those other models?
No, we don't. We don't want to do that. We just want to run one model and call it good, or run a series of models and call it good. But this is what's happening. What like the stat community does to try to figure out whether or not what you're running for one model is worth running in the first place. So that's really what we're trying to do. There's a whole. This is sort of the kind of the entry point into kind of the theoretical statistics side. I don't want to get too far in there, but I just want you to know that conceptually there are reasons why we want to be able to show this mathematically so that we can make claims about our data that we can believe, right? So, okay, that's why. So these are some of the properties. There's more properties out there, but because of this, because they're so nice, these properties are so nice, they're friendly. That's all I'm saying. They've been around a while. I mean, people developed a lot of this. The results for this in statistics were developed in the 1930s, right? Before computers. I mean, that was pretty cool, right? I mean, to be able to do that. So they've been well studied. It's that's where we're at with what we do. Okay. So where do these estimates come from? Fiscal distributions. We are dependent. The maximum likelihood estimator has to have some type of distribution for each outcome to be able to be formed. Without that, it doesn't really have anything. There's no likelihood function. The distributions provide us a likelihood function itself. So for instance, we're going to start with this univariate normal distribution. Right? How many of you had seen this formula before I talked about it over a lecture? It's pretty scary looking, right? Right? But that formula draws the bell curve, right? And just to disentangle parts of it, there's a mean right there, which tells you where the center point of that is. And there's a variance that shows up here and here, and it tells you the width, kind of how spread out it is. And this thing out in front makes it so that the area under this curve is 1. Right? And so we use that to define a probability space that we can talk about probability with. So that's sort of where all this fits together. That's why it looks so ugly, really, to try to make sure the area fits. And so last week, or in the online lecture, we pretended that, if we knew mu and we knew sigma squared, if we knew what those were, if we plug in a value for x, we can take a look at its height, right? This is what we had from it. Right? We had a mu, let's say the blue line here has a mu of 0 and a sigma squared of 0.2. That's this blue line in the middle. Now with that blue line, if we had a value right at mu, we could go and figure out the height of the curve. The height of the curve is a likelihood. Right? That's actually what we're going to get from this. We're going to do the same process here with what we do with statistics. Right? Are we good with that? Right? Sort of. Like, I don't need you to go and memorize this. I don't want you to do that unless you really love statistics. And that's cool. I've got a tattoo of it. I get it. Right? It's just what happens. But I know, you're part of the business. It's sort of, when you get a PhD in my field, they sort of do that. It's like, here you go, right? But no, really, any distribution works this way, right? Distributions have parameters, right? Like a mean, variance, sometimes things you've never heard of before. They're just out there. They're just things that have to show up in the distribution that govern kind of its shape, right? And you plug in a piece of data with those parameters, and out comes a height, right? So we can draw this curve by plugging in values of x for our data across the entire x-axis. That's how we get the height of the curve, right? So if you can understand that, plug in parameter and data, get height, you can understand maximum likelihood. That's what works. That's the core of it. And you saw last week in the distributions lecture, we could have a distribution that's not continuous. We could be categorical, right? It could be something that looks like this. Two categories, right? So if there's a 0 or a 1, I don't know, maybe this is, again, passing some type of exam. If you go say, I'm going to plug in, I have somebody with a 1 here, I'm going to go plug that in, it's going to return to you the height of that distribution. With a categorical distribution, we call that probability. With a continuous distribution, we call that relative frequency, relative likelihood. It's a relative sense in a continuous distribution where it's actually probability in a categorical distribution. How we doing? Sorry, esoteric, I know. But here's the point. Last week, we said, I know the following. Actually, we saw this was a slide from before. Assume we know the mean was 114.4 and the variance was 5.29. So if I did that, and I can plot this bell curve, this normal distribution, and if I plug in a value of 110, it's right here. The height is right there. The height is 0.028, right? In goes data, out comes height. Right? Similarly, if I plug in a value of 114.4, it's right at the mean, it gives me this height. So between the two pieces of data here, 114.4 versus 110, because one is a different height than another, we would say the one that's taller is more likely to occur relative to the one that's smaller. Right? The actual numbers themselves, the 0.17 and the 0.28, are relatively meaningless by themselves. They're not probabilities. They're just relative frequencies. So this week, though, we're going to flip this in reverse, this lecture. We're going to say, yeah, I don't know sigma squared, and I don't know mu. I don't know these two things. But I did observe a bunch of data. Right? This is one observation. It's hard to see with one observation, but I can do it with a bunch of observations. If I can do this with a bunch of observations, I would go pick a mu that would give me a height. I have all my data. I pick a mu, I pick a sigma. I plug it into each of the observations and each of this function, and it's going to give me a height for each of those. And so now I have something I can go and figure out that gives me the most likely value of mu and sigma for the data I have. That's the process that maximum likelihood works like. Right? We find the parameters that give us the most likely solution, that give us the highest value in this likelihood function. Weird? Why are you hearing this? Man, I promise it gets better. So, how we do that, we have to build what's called a likelihood function. A likelihood function is something that provides a height for our two parameters, for mu and sigma in our case, in this example. Right? So if you plug in mu and sigma, you get back a height. That way you can try out new values of mu, take guesses. New values of sigma. Take guesses between the two. Each guess that you plug in, it gives you a height for. And those likelihood functions, wouldn't you know it, start with the PDFs, the density functions, the curves that those distributions give us. And because every distribution has a PDF or PMF if you're in a categorical sense, then any distribution is valid to be put into this type of process. So what we end up building is this likelihood function across all of our observations of the sample. Okay? We have observed the data. We know what that happens to be. Right? That's one part of this function. We know right over here, we know x, that one. So each person, we plug in their x into their little function. And we do something with all of them together to build what we call a joint likelihood. And we talked a little bit about joint distributions, the likelihood of multiple variables occurring simultaneously. This is what we're building. It's a joint distribution effectively for our mean and our variance. So once I get done with this slide, by the way, I'll give you a break, try to break up the monotony of math. So we're going to take the entire sample and build this likelihood function. And we'll start off with this maximum likelihood observation. How about I take a break here? Should we do that? Take a pause, 10 minutes, get up, clear the mind, we'll come back. Thanks, everybody.